talking about local extrema. So this is still section 4.1. To get all my windows open. Here is the chat. Okay, here we go. So last class we talked about critical numbers. So critical numbers were numbers where the derivative is either 0 or undefined. And we're going to do a little bit more today with finding those. And we saw this theorem that says local extrema, so those are maximums or minimums, are always at critical numbers. But critical numbers don't always have local extrema. So we left off looking at this handful of graphs, which there's a similar graph on page 245. It's not exactly the same, but in each graph below, C is a critical number. So in all 5 of these, and I'm going to make this bigger so we can sort of zoom in a little bit. C is a critical number. So C is sort of the number we're focusing on each of these. So this is C on each of these graphs. So on these top 3 graphs, we have local maximum and local minimums. So each of these are local extrema. All of them either have a highest point or a lowest point. Whereas, I'm going to scroll down for a bit, these bottom 2 graphs, these are still critical numbers. C is still a critical number here because the derivative is either 0 or undefined, but these 2 are not local extrema. So in each of these, we can see the graph is sort of stopping for a minute, but then it keeps going up. And there's one thing I want to highlight about the difference between these 2 and their relationship between being local extrema or not. And that is, if we look at the derivative, which means the slope, so there's a C. If we were to make a sign chart of f prime, so we were making sign charts of f prime in the last class, which means we'll just write where it's positive. So f prime is positive here because the slope is positive, the function is increasing. But then on the other side, of that critical number, the slope is negative. And if we made a sign chart for f prime of x for each of these, we would find that on this one, it is another maximum. And the slope is positive on this left side of C, and then it's negative on the other side. So it's going up, and then it's coming down. And on this last graph, we're starting decreasing, but then the function starts to increase. So on these 3 graphs of local extrema, whether they're maximum or minimum, the sign of f prime is changing because the graph is either going from increasing to decreasing or decreasing to increasing. Whereas if we look at these two that are not local extrema, they're not minimums or maximums. If we made a sign chart for F prime, it's positive because it's increasing. It's 0 right in the middle there, but then it's still positive. So it never changes from increasing to decreasing. Same for this one. F prime is positive the whole way, aside from that one little critical number. So the key here to note is that at all of the maximum and minimum, the sign of F prime is changing from either positive to negative or negative to positive. So I'm going to write that in words in just a moment. And we can think of it too. I always think of these functions as like being roller coasters. So you can only reach the top of a roller coaster if there is an up and a down. If you're just going up and up and up forever, there's no top, there's no maximum. So we have to go up and down in order to have a maximum height. And the opposite is true. And when you're on a roller coaster, there's times when you sort of hit the bottom and then start going up again. And so in order to have that minimum height, we have to go down and then start to go back up again. So in words, let me make this bigger.
Is it safe to say if the largest exponent is odd, then it will never have a local extrema? And if the largest exponent is even, then it will?
It's not, because if we could have an x cubed, which we're actually gonna see an example of it in just a minute, that kind of goes up and down and up again. If it's just x cubed, like this bottom left graph looks like it could be an x cubed with nothing else on it, then it won't have a local extremum. But we can have up and down. So this is the key here. So if there is a local extremum at C, which is going to be a critical number, then the sign of F prime changes at C, either positive to negative or negative to positive. So let's do an example of finding local extremum, and we're gonna, within that, have a little bit of review of finding critical numbers and making sign charts and getting to the local extremum. So here is a cubic. So we have this function and 3 questions. So I will give you a minute before we start. Okay. So we have this function and we have 3 parts. So we need to find the critical numbers. That's what we were doing on last Thursday. We need to find the intervals where f is increasing and decreasing. We were also doing that last Thursday. So those 2 will be a little review. And then C is to find the local maximum and minimum. Maxima and minima. Okay, so finding critical numbers. In order to find the critical numbers, what is the first thing that we should do? Yes, exactly. Find the derivative. The critical numbers come from the derivative. So this is just a polynomial. So here is our derivative. So what are we going to do with that derivative now to find the critical numbers?
Factor out the 3.
There's one thing we need to do before we start that, but yes.
Set it equal to 0?
Set equal to 0, yes. I suppose we could factor out the 3 to start off with, it wouldn't hurt it, but I would set it to 0 first. So critical numbers are where the derivative is either 0 or not defined. This derivative is just a quadratic. There's nowhere where this is not defined. There's no denominator or anything like that. So we will just set it to 0. And we can factor out that 3. And now that 3 can just go away. We can divide both sides by 3. So we're setting that derivative to 0 and just solving. And this is factorable, yes. So to multiply to a positive 8 and add to a negative 6, we'll have -4 and -2. So the one thing that we just have to be careful of, and in polynomials, this is not as much of a worry, but we should get in the habit of checking, is that once we set that to 0 and solve, these are only critical numbers if they are in the domain of our original function. And they are, because our original function has a domain of all real numbers. So we're safe. When we do more complicated functions, that's something we need to be careful of. So these are in the domain. So so these are our critical numbers. A lot of people like to abbreviate critical numbers with just CN, which is fine if you want to do that. Okay, so we set the derivative to 0 and solved, and since those numbers are in our domain, those are our critical numbers. So our next step is to find the intervals where f is increasing and decreasing. So we did this on Thursday as well.
We do a number line.
Yes, exactly. So we can make a sign chart, which is a number line of f prime. So 2 and 4 are our partition numbers or critical numbers. So last time we saw we can just choose whatever numbers we want to and plug them into our derivative and simplify and find if they're positive or negative.
0, 3, and 5.
That sounds good to me. So on this section we have 0, here we have 3, here we have 5. So f prime was 3x squared minus 18x plus 24. And you can use the version with the 3 factored out as well. So if we plug 0 in there, we're just going to get 24. So that's nice. That was a good one to use. And that's a positive. So that means that this whole section is positive. I'm just going to move this f prime of x up so it actually matches the signs. There we go. F prime is 0 at 2. F prime of 3. So that is going to be, did I mess up
Is it
somehow?
8 times? Yeah, 8 times 3 is 24, not 54.
That's an 18 times 3.
Oh, okay. Then you're right.
Let me see what I did. Okay, yeah, this is fine. So that's a -3. So we should at least just get a negative. So if you use the version with the factored out 3, you should still get a negative number. And f prime is 0 at 4. And then with a 5 in it. And then we'll just plug that one into the calculator. And we get a 9. So that is now positive. So we have these sections of f prime, positive up until 2, negative between 2 and 4, and then positive after 4. So this question was actually asking where is this function increasing and decreasing? So on what interval or intervals is it increasing?
Negative infinity to 2 and 4 to infinity, and
Yes,
decreasing 2 to 4.
exactly. So a negative derivative means a negative slope. So it's decreasing between 2 and 4. A positive derivative means a positive slope. So it's increasing negative infinity to 2 and 4 to infinity. So those two parts are things we did on Thursday. So now we're adding in this local extreme. So we want to find the local maxima and minima of F, if there are any. You might have homework questions that ask that, and there might not be either or not be one of those. So we can use the work we just did in the sign chart.
It's really choppy. Just FYI.
Thank you
It might
for
just be me, though.
telling me. Is it super choppy for anyone else?
Me too.
Yeah.
Yeah, you're cutting in and out.
Ugh. Let me do this. Okay, let's see if that helps. Did what I just did help at all? Is it still choppy?
On
No, it
mine?
sounds better.
Yeah, you sound better.
Okay, great. So let's see how this goes. Okay, so I'll go back to where I was. So we, on C, we're finding the local maxima and minima. And so we can use what we did in part B to do that. And so just for the sake of being able to make some notes, I'm going to rewrite that sign chart, or at least a simplified version of it. So we had 2 and 4. F prime was and positive here. So if we just imagine this graph, we don't need a whole lot of details at the moment, but if we just think about what's happening here, the graph is going up, 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 up until 2, and then it's going down, and then it's going back up. So where do we have a local maximum?
At 2.
Exactly, at 2.
It's doing it again.
So on, oh, it's, am I choppy again?
You're caught up now. Yeah.
Let me try turning off my video and see if that helps. Okay. So on our sign chart, we had positives and then it turned to negative. So our graph goes up and then down. So we definitely have a local maximum at x equals 2. And where will we have a local min?
4.
Exactly.
Unless,
So we're just,
no, is it also considered, sorry, is it also considered a minimum because it's coming from the negative infinity or no?
no. Because that negative
Okay.
infinity is just that whole interval. So the negative infinity to 2 is one of our increasing intervals, but it doesn't actually matter where the interval starts. What matters is that right at 2, it's changing from going up to going down. So we have a peak there, and it's not actually sharp.
Okay, that makes sense.
And on this one at 4, we're going from down to up. So this is another one I always think of a roller coaster. So if we're starting going down and then starting to go up, we've hit a bottom. If we're starting up and then start to go down, we've hit a peak. So we know the X values where there are maximum and minimums, but we haven't actually found the maximum and minimum. So remember, those are the Y values. So the max is going to be f of 2, because that's the Y value of the function at the point 2, at the X value of 2. And so here we're going all the way back to our original function. Because we're looking for the peak on the actual graph itself.
So then we just
Sometimes
plug
people
and
just-
solve.
Right, exactly. So a lot of times people will forget to find the Y value, but that's actually what the maximum is. So f of 2 is 2 cubed minus 9 times 2 squared. Oops. And then we do the same thing for the min. Going to do that in the calculator.
$64 minus 72 plus.
I got, oh, I just did it in the calculator and the result is 6.
Oh, okay, gotcha. Much easier.
So when we get these two numbers, our actual local maximum is 10 and our minimum is 6. In general, it's nice to report them as in function notation. So we have a local max of f of 2 equals 10 and a local min f of 4 equals 6. So our sign chart tells us where the local max and or min occur. Then we have to plug them back into the function to find out what those actual y values are. So this is an example of a cubic, a degree 3 polynomial that does have maximum and minimum because it's going to look something like this. And right now we are not going to graph it in a detailed fashion, but it has this local maximum and minimum. So it has that big up and down. So this is all of section 4.1. And so 4.1 was titled First Derivative and Graphs in section 4.2. So here is our first question that I just want you to think about for a moment. We have two graphs here. They're both going up. What is happening to the derivatives or the slopes of the following graphs as x increases? So as x starts to get bigger in each of these, what is happening to the slope or the derivative?
That's the first one's going up in a positive manner and the second one's going up in a negative manner.
What do you mean in a positive and negative manner?
I would assume that it would be like a plus versus a minus.
It is going to have something to do with that, positives and negatives. But both of these, oh, sorry, go ahead.
Is decelerating?
Yes. So each of these is going up. Both of these slopes is positive. They both have positive derivatives because they're increasing. But on this one, the slope is accelerating. That's one word for it, which means the slope is speeding up, basically. The slope is getting steeper. That looks like it's misspelled, but I'm going to leave it. Whereas on this other one, the slope is actually starting to get flatter. So it's like it's slowing down or decelerating. We're still moving. The function is still increasing, but the slope is getting flatter. So not only do we care about whether the function is increasing or decreasing, because both of these functions are increasing, but we also care about what is the derivative doing? Is the derivative getting steeper? Is it increasing, or is the derivative flattening out? So in this first case, f prime is increasing. The slope is actually increasing here. It's getting steeper and steeper, and it's already positive. In this other one, f prime is decreasing. So these two shapes have names as well. And those are about the concavity of a graph. So I'm just going to leave this here for a moment before we unpack these two definitions. Okay, so the concavity of a graph or a piece of a graph refers to if, basically if the first derivative is increasing or decreasing, and they look like this. So we say a graph is concave upward or just concave up. That's usually what I say. On an interval, if f prime is increasing on AB. So if f prime is increasing, then we say the graph is concave up. If f prime is decreasing, the graph is concave down. So concave is a word that's not just used in math. So if we have like a concave lens, if you take like physics or another science class, concave just means it's like pushed inward, like a cave. And so concave up and concave down is referring to which direction the cave part is opening toward. So this first graph is concave up. And mathematically, that's because the derivative is increasing. Visually, it's because the concave part of the graph, the part of the graph that's curved, it's curving towards the upward direction. Its cave side is up. Whereas the other side is concave down, or this other graph is concave down. Because now, if we're inside of this cave, that inside part is going down, is pointing down. I've heard people say that concave up looks like a smiley face and concave down looks like a frowny face. So if that's helpful, then that is a great way to think of it as well. So when we were looking at just regular functions back in, when we were looking at whether a function is increasing or decreasing in 4.1, we looked at whether the derivative is positive or negative. So if we want to know if the derivative is increasing or decreasing, which we do here, we need to know whether the derivative of the derivative is positive or negative. And so we have one little concept called the second derivative. And just before we get into this, is my sound better? Am I still breaking up or anything?
It seems like it's better, though that might just be the traffic rather than you.
Yeah, it's better.
Okay. I'll just leave my video off then, and I will try to limit my hand gestures since you can't see them. Okay, so the second derivative, which is referred to as f double prime, that's how we read this. And I've lost it. It is. So the second derivative is just the derivative of the derivative. So we just take the derivative twice. So we don't need any new derivative rules at all. Everything we know about derivatives still applies here. We're just doing it 2 times. So if we want to find f double prime of this function here, we would first find f prime, the derivative, using our power rule. And then we would do the derivative again. So the derivative of f prime. So now we have 24x plus 4.
And what does this do?
This is the second derivative, and which we're going to use for concavity in a minute.
Okay.
Oops. So the second derivative is just the derivative of the derivative. So we just do the derivative twice in a row. So we're going to leave that for now. We'll do a couple more examples of second derivatives when we're applying them to these graphs. But so I'm just going to go back for a moment. Conceptually, so I'm going to actually go back too. So this was the problem we were doing before. In order to find where the function is increasing or decreasing, we found where the derivative f prime was positive or negative by making a sign chart. So for concavity, we need to know whether the derivative is increasing or decreasing. So if we want to know if something is increasing or decreasing, we have to take the derivative of that and see if it's positive or negative, which is why we need to use the second derivative. So here's a little chart relating concave up and concave down. So concavity refers to the shape of the original function, f of x. And it means specific things for the first derivative of the function and the second derivative of the function. So on the previous page or 2 pages ago, we said that a graph is concave up if f prime is increasing.
Increase
Yes, exactly.
and decreasing.
Right, exactly. So for concave down, f prime is decreasing. So that is conceptually what's happening. But if we want to actually do some math and investigation on the function to figure out where this is happening, where f prime is increasing and f prime is decreasing, we need to use f double prime, or the second derivative. So if the first derivative is increasing, what can we say about the second derivative?
I'll take the roller coaster down.
Yes, not quite. Sorry, my excitement was a little premature. So if
Good guess, though.
if f prime is increasing, f double prime, so just for a moment, I'm just gonna erase 1 prime from each of these. If we were just talking about the first derivative and said, or excuse me, the function f is increasing, what would that mean for the first derivative?
It's increasing.
Not quite.
Are you asking what's happening to the graph?
No, we can say something more specific about f double prime. So I'm going to go back for a second to our first.
Is it the inverse?
Not the inverse. We don't. Not quite. So we were able to find that f is increasing on these intervals because the derivative, f prime, was positive there. Which means, so if f is increasing, f prime is positive. So if f prime is increasing, then f double prime is positive. So any function increasing means its derivative is positive. So here, f prime is its own function. So if f prime is increasing, f double prime must be positive because we're just doing the derivative of f prime. So if f prime is decreasing, what can we say about f double prime?
Less than 0.
Yes, exactly. F double prime is negative. And this actually is, if we're looking at a sort of a specific situation, the words acceleration and deceleration were brought up earlier, and this is actually what's happening. Acceleration means the second derivative is positive, we're speeding up. Deceleration means the second derivative is negative and we're slowing down.
So it's basically doing the same thing from prime to second prime. Is that
Yes.
correct?
Yep, exactly. Exactly. And all pretty much all of our techniques that we were doing in 4.1 are going to apply in 4.2 as well. We're just going to be using the second derivative instead of the first. So this is all just sort of building on the same kind of concepts. And so graphs that are concave up, or parts of graphs that are concave up, it might just be a little piece like this. It can also be going down. So even though this little piece that I just drew is decreasing, it's still concave up because that little smiley face is going up. And we can also
so
have
no
graphs.
matter if it flips across the axis. Is that kind of how it is?
Sorry, my pen is drawing on its own for some reason. So so the concavity is based on whether that opening part, the opening of the curve, is going up. And so it doesn't actually matter if it's like opening to the right or to the left. It's whether it's up. And so we could have like a parabola is just fully concave up because that whole time it's curving upward. But we might just have pieces of graphs that are concave up, and each of these to the left.
So if that parabola was upside down, then it would be concave down.
Exactly. Yes. So some graphs like these parabolas are fully concave up or fully concave down, but most graphs are made up of pieces and they change their concavity, which is what we will be doing in this section, is figuring out where graphs are concave up and concave down. So let me make sure, okay. So I'm gonna put up another sort of chart just to get all of this stuff, get a little more practice with all of this increasing and concavity things. So the relationship between increasing, decreasing, and concavity. So here are 4 parts of graphs, actually. I better leave that for a second. All graphs, as long as they're not like, all graphs that aren't lines. So if they have flat parts, then this doesn't apply, but any graphs that are curvy are made up of these 4 types of pieces. So this is the relationship between a function being increasing or decreasing and its concavity. And I labeled these A, B, C, and D because I'm gonna put up a poll in just a minute to ask some questions about A and then B, C, and D as well. So these 2 top graphs are concave up, and these 2 bottom graphs are concave down. So if we use that like smiley face, frowny face example, if we put eyes above the graph, those 2 downs look like frowns. And if we put eyes above the graphs, the 2 ups look like smiley faces. So that is relates the up for smiley and down for frowny. But then we also have the difference between increasing. So we have increasing on the right. Both of those graphs are going up. And then decreasing on the left. Both of those graphs are going down. So I am going to put up a poll specifically about graph A. So just focus on A for a minute. And the poll is going to ask, let me move that. What can we say about whether F prime is positive or negative and whether F double prime is positive or negative? So your poll, let me put it up while I explain. So this poll has 4 choices, and it says, which of the following describe graph A? So it has F prime being positive or negative and F double prime being positive or negative. So which of those combinations fits graph A in the top right? So about 15 seconds or so if you haven't answered yet. Okay, I am closing the poll. Okay, so 72% chose the correct answer. So before I don't know why you wouldn't have gotten the poll. We'll see if it shows up on the next one. I'll make a note of that though. Okay, so we have two things that we know about this graph A. It's increasing and it's concave up. So increasing tells us about the first derivative. So if it's increasing, the first derivative is positive. That slope is positive that whole way on that graph. If it is concave up, I'm just going to write up for short. Well, no, I should write concave. Then the second derivative is also positive because the slope is getting bigger and bigger and bigger. The slope itself is increasing. So that one, concave up and increasing, has both the first derivative and the second derivative positive. Okay, so that one looks good. I'm gonna put up a poll about the second one now to see how that goes. Okay, so I'm gonna close the poll in just a second. So this one was closer. So let's look at this one. So graph B is concave up and decreasing. So if a graph is decreasing, does that mean that the derivative is positive or negative?
Negative.
Negative, exactly. So the decreasing part tells us that f prime is less than 0. And we also know that this graph is concave up. So is f double prime positive or negative?
Positive.
Positive, exactly. So that one was the third choice on there. So decreasing means the first derivative is less than 0. Concave up means the second derivative is less than 0. Or greater than 0, sorry. Concave up means the second derivative is greater than 0. Okay, so we're gonna keep practicing on these. So now we're on graph C, and that C is a little bit hard to read. So graph C is concave down and decreasing. So let me put up one more poll. So same choices. Graph C, concave down and decreasing. So 15 seconds. Closing the poll in 3 seconds. Okay. So looks good. Most people chose the correct choice here. So if the function is decreasing, that's the same as the one above, which means the first derivative is less than 0. So decreasing always means f prime is less than 0. If the graph is concave down, now our second derivative is less than 0. So that f double prime is less than 0. So in this case, both are less than 0. All right, last one. About 15 more seconds. Okay, I am going to close the poll. All right, this looks good again. So I think that was getting easier as we did a few more. And there's only one choice left, but still. So increasing means our first derivative is greater than 0. So that's the same as the one above it. Increasing means f prime is positive. Concave down is the same as the one to the left, which is that f double prime is less than 0. So all of our graphs that we are going to look at, and we're going to start more serious graphing next week, where we're putting all of this together. All of our graphs will be made up with these 4 basic shapes: concave up and decreasing, concave up and increasing, and the other 2. And it all comes from these facts about the first derivative and the second derivative. All right. So one last thing that we need to know for this section for now is about inflection points. So inflection point is actually a word that we use in regular life sometimes as well, and it's usually some time where a change happens. And so in math, it's specifically an inflection point is a point on the function where the concavity changes. So that means it either changes from up to down or down to up. And I want to highlight this on the function part. It has to be in the domain. So this is sort of analogous, not exactly the same, but analogous to our critical points. Not exactly the same, but it's sort of a similar type of thing where we'll have a similar process to find inflection points as we had to find critical points in 4.1. And so I'm going to put up a few steps to finding inflection points, and I'll just leave this here for a minute, and we're going to go through these steps on 1 or 2 examples today. So for finding inflection points, we need to find the partition numbers for f double prime. So in 4.1, we found the partition numbers for f prime. Now we're finding them for f double prime, which means where f double prime equals 0 or where f double prime is not defined. Then we'll make a sign chart for f double prime. So these 2 steps should seem similar because we're doing basically the same thing we did in 4.1, but now we're just doing it for the second derivative instead of the first. Then 3 is where it changes a little. So if the sign of f double prime changes at a partition number and the number is in the domain of f, there is an inflection point there. And our last step, so inflection point, it really is the whole point, the x, y. So we need to find the y values that go with the inflection points.
Can you elaborate on 3 when we get there?
Yeah, yes, yeah. So we'll do
Okay.
an example to see what that means.
Okay.
Yeah. So let's get to our first example. So we're going to find the inflection point or points of this function. Which is the same one we were working with before. So to find inflection points, we need to know the second derivative. So to find the second derivative, we take the first derivative first. And then we just do the derivative again.
I assume there wouldn't be instances where when you take the first prime that you're only left with a constant, but is that possible?
It is possible, but not, that won't happen if we're finding inflection points because there would be no inflection point there.
Okay.
If we took the first derivative and we're left with just a constant, that's just a line.
Oh, okay.
Yeah. Lines are great, but we're not working with them in this chapter, so we won't see that. So our first step is to find the partition numbers for f double prime. So we have f double prime, but we need to know where it's 0 or where it's not defined. This f double prime is always defined. There's no denominators or anything like that. So we can just set it to 0.
So x equals 3.
Yes, exactly. Well, that 3. So there's only one partition number here. And that is at x equals 3. When we're working with polynomials, when we do the second derivative, they tend to get much simpler, or they do get much simpler than the polynomial we started with. So solving those is usually pretty nice. So we have a partition number, but the inflection point is specifically where the concavity changes. So steps 2 and 3 are looking for that. So for step 2, we will make a sign chart for f double prime. So we were making sign charts for f prime in the previous section. And so this will work exactly the same way. So now we only have one partition number, or 3. And we can figure out where f double prime is positive and negative, because we know that that's how we figure out if it's concave up or concave down.
So 0 and 5.
That sounds good. So less than 3, we can choose 0. Greater than 3, we can choose 5. So I just put that 0 above the 3 because we know that the second derivative, f double prime, is 0 there at 3. So same thing that we did before, but now instead of using f prime, we're using f double prime, and we'll just plug in these numbers we just found. F double prime was 6x minus 18.
Negative 18.
Mm-hmm. So we have a negative second derivative. And on the other side, f double prime of 5.
12.
Yes, so we have a positive.
Is there ever an instance where it would stay negative on both sides?
Yes.
Okay.
Wait, yes. It's possible.
Then that line would just continue going in whatever direction it was going, I assume.
Since we're talking about the second derivative in this case, it would mean that the concavity does not change.
Okay. But it still exists.
Yes.
Okay.
So here, before, let's just take a little side note and think about where this graph is concave up and concave down. So on what interval is this graph concave up?
Zero to infinity?
Not 0. What's our partition
Sorry,
number?
3. 3.
Exactly. And that's because f double prime is positive on that interval based on our sign chart. And so it's concave down on the other part of the graph, negative infinity to 3, since f double prime is negative. So this problem didn't explicitly ask for those intervals, but I just wanted to highlight that. That's what we were practicing on those graphs before. F double prime being positive means it's concave up. F double prime being negative means it's concave down. So what we need to note here is the sign of F double prime changes at 3. I'm going to write at x equals 3 to be clear. Which means the concavity of F changes at 3. Let me move this away. So when we made our sign chart, we had that partition number of 3 because the second derivative is 0 at 3. And we saw that the second derivative is negative on the left side and positive on the right side.
So then do we take the 3 and put it in the original equation?
Yes. So let me
Okay.
scroll back up to our steps. And there's one more thing we should check. So on this number 3, so if the sign of F double prime changes at a partition number, we have that. Our sign of F double prime changed from negative to positive. And the number is in the domain of F. So we also need to check that. But since this, our original function is a polynomial, its domain is all real numbers. So it's definitely in there. That means there is an inflection point there. So we definitely have an inflection point at x equals 3. And our last step is to find the y values of that inflection point, which means just plug it into the original function.
Will you do one where it shows that the domain is not?
Yes.
So we can see the difference? Okay.
That is our next example.
Okay. Thank you.
Yep. So we have these two conditions where the sign of F double prime changes and that x equals 3 is in the domain. So there is an inflection point at x equals 3. Oh, and I didn't mean to cross the L on inflection. So our inflection point is the whole point x, y. So we do need to now find f of 3. So to pull, oh, plus 24 minus 10. Oops. And we have 8.
You crossed your L.
Don't know why I keep doing that. Thank you. So this process is very similar to what we were doing in 4.1. We're just finding something else. So we have to do a little bit different stuff. Okay, so that one was a polynomial, and polynomials are generally the nice ones to work with because taking their derivatives are nice. Solving them is usually nice.
Will we see square roots and like natural logs and things of that sort?
We won't, not in this class.
Okay.
We will see rational functions, which is our next example, but there, yeah, I think there is, I'm gonna put an extra credit problem on the next homework that has some rational exponents, which are radicals, but mostly we'll be focusing on polynomials and rational functions. So this one is going to be a little bit of practice for your test on Thursday, because when we're doing the derivative of this, we're going to need to use a few rules that are on that test. So if we want to find the inflection points of f of x equals x plus 2 over x minus 2, we need to find the second derivative, which means first finding the first derivative. What rule do we need to use to take the derivative of this function?
The division.
Yes,
Quotient.
quotient rule. Yeah, exactly.
Thank you.
So our quotient rule is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Oops, sorry, I meant to write b of x squared. Got ahead of myself. So we can identify our top and our bottom. So the top is just x plus 2. The bottom is just x minus 2. And t prime and b prime. So these are nice. This one looks like it might be kind of tricky to get the derivative, but the t prime is just 1 and b prime is also just 1. So then we just need to fit all of that into our derivative formula. So we have the bottom, x minus 2, times the derivative of the top, which is just 1, minus the top, which is x plus 2, times the derivative of the bottom, which is just 1, all over the bottom squared. So simplifying the top, we have x minus 2 times 1, which does nothing. Be super careful with that minus sign on the top. That was the thing that people were making a mistake on the homework. That negative needs to distribute to everything after it. So the 1 isn't going to do anything, but that's a minus x minus 2.
Quick question, is that first part of the equation, is that x minus 2?
That is
Yep.
2.
Yeah.
Thank
it is.
you.
There you go.
Don't know where that 1 came from. Thank you.
That's what I did on the last test. I missed a 1.
And x minus 2 squared. So now we have x minus 2 minus x minus 2. So that top is going to simplify a lot. Those x's completely cancel each other out, x minus x. And the 2's, negative 2 minus 2 is negative 4. So that is the quotient rule to get the first derivative. But we're trying to get the second derivative.
You have to do it all over again.
Yes. And so you can actually use the quotient rule here. I would change this a bit to use the chain rule if it were me. So since we already did some quotient rule practice, let's use the chain rule. How should we rewrite f prime here so that we can use the chain rule on it?
So would that be the -4 and then plus x minus 2 negative 2 to the -2 power?
Times.
Yes,
yeah.
it'll be times, but you're right. We'll bring it up so it'll be a -2.
Yep,
Exactly.
there you go.
Yep, exactly. So now we have, instead of having a quotient, we just have that -4 times the thing next to it, which is nice if it looks like a quotient, but there's just a constant on top like here. I think there's no point in going through the quotient rule because then it'll be a little messier than necessary. So to take the second derivative of this now, the derivative of the derivative, we can use the chain rule. So that -4, we don't really need to pay attention to in the chain rule because it's just going to multiply with whatever comes out of it, but you can put it in there. So I'll put it in here just so it's apart. So we have the interior is going to be that whole x minus 2. So we have -4 times I of x to the -2. And then I of x is that x minus 2, the interior. So the derivative of the exterior, this is just a power rule. We have a thing raised to a power. So we'll take that power, multiply it down. So -4 times -2 is +8. And that power is going to lower by 1. So we'll have a -3 there.
And that's just 1.
Yes, I prime is just 1. So putting that all together, so now this is f double prime that we just found. So that's 8 times I of x is in there, x minus 2 to the -3. And this, we are going to need to do some solving. So on your test, you don't have to do this if this came up, but for this, we should put it back on the bottom so that we have a positive exponent.
Sorry, I missed it. Did you not include the second, like the I prime of x? Because it's 1.
Oh, I'm sorry. Yeah, that was just my brain doing it without actually writing it down. You're right. It is just 1, and so that's why I didn't include it, but I should have written it so that it's clear that that's what we're doing. Thank you for pointing that out. So our chain rule, we have that e prime with the I inside of it, and then we're multiplying by I prime. But since it's just one, it's not affecting our result.
Right next to the chain rule, can you just write the formula?
Yes, so it's e prime of I of x times I prime of x.
Thank you.
Mhm. So let's scroll up a little bit. So this problem, we're starting with f prime, or excuse me, f, which is this quotient. So to find the first derivative, we used the quotient rule, t and b and t prime and b prime, and put it all in and simplified. Then to find the second derivative, we were able to use the chain rule to get that. So quotient rule and chain rule will both be on the test on Thursday. So that was only a little tiny part of this actual problem that we're doing now, which is to find the inflection points. So partition numbers are what we're looking for. So partition numbers of f double prime are where either f double prime equals 0 or f double prime does not exist. So we saw an example similar to this one on last Thursday that was just f prime, but we have a sort of a similar situation here. So if we set f double prime to 0, a fraction can only be 0 if its numerator equals 0. So if we just have an x, or if we just have an 8 up there, that's never going to be 0. So this one is no solution. We can, however, figure out where f double prime does not exist by setting the denominator to 0. That should be a 2, excuse me. So it does not exist whenever the denominator is 0, so we can set that denominator to 0 and solve. So if x minus 2 cubed equals 0, that means x minus 2 must equal 0. Or we could think of it as taking the cube root of both sides, and cube root of 0 is 0. Oops, that's a 2. Keep writing the wrong numbers. So our partition number in this case is just x equals 2. So let's make a sign chart of f double prime here. The second derivative is not defined at 2. It doesn't exist at 2.
Zero and
I didn't hear a second number, but I'm going to say 3. That'll be an easy one to evaluate. So f double prime of 0, 8 over 0 minus 2 cubed is going to be 8 over negative 8, which is negative 1. And f double prime of 3, 8 over 3 minus 2 cubed. That denominator is just 1. And so we're positive here. So same thing as usual, make an assigned chart, and we use our partition number to divide up the real number line. So we have our second derivative is negative everywhere below 2 and positive everywhere above 2. So the sign did change. Which is one thing that we're looking for when we're looking for inflection points. But is there an inflection point at x equals 2?
No,
No, why not?
because it's undefined.
Right, exactly. And it's not, I want to clarify, it's not because the second derivative is not defined. It's because f, the original function, is not defined at 2. X equals 2 is not in the domain of f. Because f was, I'll bring that back in a second. F was x plus 2 over x minus 2. So 2 would make f undefined. So that means there is not an inflection point at x equals negative 2, or excuse me, x equals 2, or anywhere. So 2 was our only option. Our inflection points will come from the partition numbers of f double prime, and since 2 was the only one, even though the concavity does change from one side to the other of 2, it's not defined on our original function, so it's not an inflection point. So that function just doesn't have any inflection points, and that's a thing that can happen as well.
So real quick, Madeline, in this specific equation, is that how you want us to write down that answer? Oh, never mind. There it is.
Yeah, I just realized I hadn't actually given an answer. So you would just write no inflection points, and that's it.
So would this look like Of the graphs that we were looking at yesterday, would this look like the second one on the bottom?
The graphs that we were looking at, these ones?
Yeah, the ones at the very top. So would that be the second one on the bottom?
So second one on the bottom. It's not, because that one is actually still defined at C. So the second example we just did actually has an asymptote. And so let me bring up Desmos real quick. And let's look at, oops, what's happening here? X plus 2, X minus 2. So this one has an asymptote at x equals 2, which is why it's not defined there. So there's no inflection point at x equals 2 because there's just no function there. But we can see that this left side of the function is concave down the whole time because it's always that sad face if we put up eyes above it. It's all, the curve part is always pointing towards the downward side of the graph. Whereas the right side is concave up because the curve is going up. So if we put little eyes in here, we could see a smiley face. So this has different concavity on each side of the graph, but it's not defined at 2, so we can't say that there's an inflection point there. And I just want to graph the other one that we were just looking at. And if you have to go, that's okay, because we're out of time. But I'm just going to graph the other one so we can see that. So that was x cubed. Was it plus 9x squared? Was 24x minus 10, or was that a negative 9? It was a negative 9. Okay. So this one we can see we had our maximum was 210, our minimum was at 4.6, and the inflection point is right here when x equals 3, which means it's changing from being concave down. So we have this downward curve part, and then it's going to concave up where it's curving up. So the inflection point is usually a lot harder to see when we're just looking at the graph, but there's one little instance where it changes from this downward curve to an upward curve. And we'll be doing a lot more with that next week. So that is all for today. Your test is on Thursday, so feel free to send me questions before then if you think of anything, or make appointments or drop in my office hours as well. And I will see you then.